Okay, I guess we can start. Um, for today, the only topic that I left that I wanted to tell you about was these differentiation matrices, how to find them. I'll tell you how that works, which is actually like a pretty short topic. Um, and then I'll give you like a quick application just so that you see how it's used in practice, which is interesting because it's related to this like topic of differential equations we were talking about on Thursday. But um, but the application is just to illustrate the the method. I wouldn't ask about the application. I would just ask about the how to find the differentiation matrices. But it's still useful to see how it actually is used in practice. Okay, so the last topic is differentiation matrices. Okay, and so what is the idea? So so far as you have seen, like I think like probably 70% of the course can be summarized in like finding the correct polynomial, approximate a problem, the solution of a problem by finding an appropriate polynomial. So polynomials have like been like very important for us um throughout the course. And one of the nice things about polynomials, right, is that they are easy to either integrate or differentiate, right? So polynomials are useful ways uh, to approximate a solution to a problem that we care about, um, in part because due to the fact that finding the derivative or the integral of a polynomial is relatively easy. That so like I mean, basically you can write any polynomial that you want. Like you could write whatever polynomial you want. Like let's write like something of degree 4, I don't know. And like finding the derivative is almost like, you do it term by term. And so, like in a sense, like it takes very little time. But that is true. But one of the things we have been doing when we were finding polynomials is that when we were finding polynomials, we were using the Lagrange form of the polynomial, right? Uh, but um, when finding polynomials, and maybe you noticed that when we were talking a little bit about how to approximate the derivative, using Taylor's formula and polynomials. But if you write the polynomial in the Lagrange form, then finding the derivative can be more tedious, than if you have the polynomial written down as like kind of like term by term. Um, so finding the derivative is more costly. So just to give you like a quick example, if you wanted to, if you were trying to find the polynomial, let's say through these points, through -1, y0, 0, y1, oops, and 1, y2. So like you have like you have the number line, you have -1, 0, 1, and then, you have some values some y values that you want the polynomial to pass through, right? So this is -1, y0, 0, y1, 1, y2, right? If you're trying to find a polynomial that goes through these points, right? If you use like the Lagrange form, I mean, it's not a super long calculation. It's not too bad to find. If you use a Lagrange form of the polynomial, then in Lagrange form, the polynomial looks something like this: 1 plus x, 1 minus x, plus 1/2 x, 1 plus x, and well, let's put the y2 here. Okay, so in Lagrange form, the polynomial looks like that. Okay, so this is the Lagrange form. And if you were to try to find the derivative of this polynomial, of course it can be done. But if you try to find it uh, written down this way, then you see it is a bit more tedious, right? Because in order to find the derivative, I mean, like you would have two options, right? Like if you want, one option would be to just, in order to find the derivative, is to do product rules, right? Like you could do the product rule here. You could apply the product rule to this term. You could apply the product rule to this term and also to this term, which is fine. Like, it can be done. Or like, another alternative would be to kind of like do like a, multiplication first, like, so recombine a bunch of the terms, and then you kind of like put it into a form that's closer to what we were doing earlier. But all that I'm trying to say is that, like, for example, if you try to find p prime, and let's just call this p of x, to find p prime of x, you either use the product rule, right? Either use the product rule, or you kind of like use you multiply out everything first to kind of like combine terms, like, or do the multiplications first in order to rewrite the polynomial as, something like C0 plus C1x plus C2 x squared. In this case, like, it would be a quadratic polynomial, right? Like a degree 2 polynomial, because I gave you 3 points. So, like, remember that the degree is one less than the number of points. And then, and if you kind of like, once you do that, like, then you could find easily the derivatives. But the point is that some work has to be done either by using the product rule or by doing all this crazy multiplication, and then finding the derivatives. Uh, okay, so the reason why I bring this up is that, so that means that in practice, like, yes, finding the derivative of the polynomial is easy, but like sometimes the polynomial can be presented in a way that requires you to do some extra work first before you kind of like take the derivatives. So kind of like the idea of like the differentiation matrices that I'm about to tell you is kind of like a way to store, since like finding derivatives actually can take a bit of time, even for polynomials, that the differentiation matrix will be a way to store the values of the derivative of the polynomial at particular points. Okay, so because again, it's kind of like a tedious process, so it's kind of like a nice way to kind of like store all that information. So the idea of a differentiation matrix. It will be a matrix that somehow that stores the values of p prime of x at particular for particular certain values of x. And I'm about to be a bit more precise. Okay, but then that will kind of like be a convenient gadget to have, because if you need to find derivatives, then you can kind of like use the differentiation matrix to kind of like compute them more quickly, and you'll see why. I mean, you'll see that in a moment. Okay, is that okay so far so good? Okay, so let me give you kind of like an example. And then I will kind of like give more like of a definition of what the differentiation matrix is. So the idea is that for like a differentiation matrix, what you will choose. So let me write down the setup first, and then I'll kind of like work it out still in this example that I was just telling you about. So for the differentiation matrix, the setup, or like the input, like just to keep thinking about it as an input, because again, we're trying to write it kind of like as an algorithm. So the idea is that you will choose some nodes. Like again, nodes is just like a number, the name for like certain x values on the number line. So you choose n plus one nodes, which I'm calling x0, x1, up to xn. Okay. And you find the polynomial. Okay, you will find the polynomial of the it will be of degree n, as always, that goes through these particular nodes and some certain y values, that passes through x0 y0, x1 y1, up to xn yn. And just for clarity, at this stage, like in this setup, you're thinking of the nodes are kind of like fixed numbers, and the y0 up to yn are like you don't give specific values up as of now. So here, x0, x up to xn will be like known numbers, like in a sense, like they're known. But you regard y0 up to yn as variables, okay? But you regard y0, y1, up to yn as variables, okay? And you'll see why in a moment. So, for example, uh, that's kind of like I was doing like a couple 2 minutes ago, where the nodes I could have chosen to be -1, 0, and 1. Okay, let me see what colors I use. So, like an example could be to use x0 to be -1, x1 to be 0, and x2 to be 1. Okay, so as you can see, they are specific values for the axis, so they are known. So these are like the nodes. And then the polynomial, then you're looking for the polynomial that passes through those 3 points, right? Like, so P2 is the polynomial through -1 y0, 0 y1, and 1 y2. And so you see here right now, as of not at this particular moment, I'm not giving specific values to the y's. I can later, but not at this particular stage. So you do that, and it is a polynomial that like I wrote like 2 moments ago. So let me just copy paste it. But like I just want to emphasize that you think of the y's as variables. So here, notice, or parameters. Maybe let's use like the word parameters to not kind of like, because like the polynomial will depend on x, right? So like they are kind of like parameters, like so you don't give specific values to them right now. Notice that y0, y1 are regarded as parameters for now. Okay, and so the polynomial is the one that I wrote a bit earlier. Okay, so the polynomial in the Lagrange form would be this. So this is the polynomial, which if you, I'm about to take its derivative. So if you were to take its derivative, it is more convenient to kind of like rearrange it so that it is, you know, it just kind of like recombine everything together. So if you kind of like recombine it, this ends up being the same as, let me see, it's the same as y0 plus y2 minus 2y1 over 2 x squared plus y2 minus y0 over 2 times x plus y0. And maybe let me change the color so that the variables like x, they are in black. Okay. Okay, that is just how you can make it look if you kind of like do the, if you kind of like use the distributive property and just like multiply everything out. Okay, so let's put x in black. And then I guess this one can be in red. Okay. And so you find the polynomial, that's kind of like step one. And then step two, as you know, as before, like if you're interested in the derivative of this polynomial, you find the derivative, and this is like the difference. Now, what I want to do is just evaluate the derivative at the nodes. Okay. So what I will do is evaluate the derivative of the polynomial as at -1, 0, and 1. So let's call that step two. So would be to find the derivative, and you evaluate it at the three nodes, and evaluate it at the nodes, well, which in this case, the nodes are x0, x1, x0 equals -1, x1 equals 0, and x2 equals 1. Okay, so let's see. I mean, it's not, that's why I chose like this polynomial, because it's not too hard to work it out right now. So if you find the derivative, what is the derivative uh, of this function with respect to x? Okay, so you get 2x here. So you get 2 times y0 plus y2 minus 2y1 over 2 times x, right? Plus y2 minus y0 over 2, right? Like this becomes 1, so I don't have to include it. And this is a derivative of a constant, which doesn't need to be included either. Okay, so that is the derivative of the polynomial. And then what I'll do, now what I'll do is evaluate it at each node. Okay, so I have the derivative and now evaluate it at each node. So I'll try to use 3 different colors for that. So I'll try, okay, so the first node is -1. So I will evaluate this at -1. Okay, so you put a -1 here. Okay, so you can work it out. If you put a -1 there, Let's see. If you put -1 here, well, I'll kind of like simplify it a little bit. You get, oh, like, ah, that's silly me. Like these two cancels out these two. So maybe just before continuing, let me simplify the formula for the derivative so that it looks a little bit easier. So it's y0 plus y2 minus 2y1 times x plus y2 minus y0 over 2. Okay. So if you plug in x equals -1 here, then you get negative y0, right? You get negative y0 here, and then there's a negative y0 over 2 here, so they can be combined, and then that gives you -3 over 2 y0. And then what do you have with y1? With y1, you have -2y1, but it gets multiplied by -1, so that becomes 2y1. Okay. And then, okay, there's a -1 here. So -1 with y2 gives you negative y2. So you have a negative y2 plus y2 over 2. So that gives you -1/2 of y2. Okay? Is that okay? Like, so, I mean, that is just what you get by evaluating x equals -1. And then, let me put the next one below. So the next one would be to evaluate this at 0. So then you evaluate the derivative of 0. This one is the easiest one, right? Because if you evaluate it at 0, if you evaluate this at 0, this is all that disappears, like this no longer contributes, right? So you just get this. So, but let me arrange it in a way that's convenient. So I'll just write it as -1/2 of y0 plus 1/2 of y2, right? And then I'll do something that's silly, but you'll see why in a moment. I'll write this as 0 times y1. Okay. So it is the same, because 0 times y1 just gives you 0. And then the last one would be to evaluate at 1. So if you evaluate the second derivative at 1, then you put x equals 1 here. Okay. You put x equals 1 there. So if you have x equals 1, you get y0 minus y0 over 2. That's 1/2 of y0. Then you get what has a y1. The only thing with y1 is this, but now x equals 1. So you get -2y1. And what has a y2? This has a y2 and y2 over 2. Like, okay, when you add them, you get 3/2 of y2. Is that okay? Is that making sense so far so good? Any questions about this? So this is also all that you get just by, taking the derivative and evaluate it at the nodes. But now kind of like, and this is how linear algebra always works. The idea is you have three equations, right? The moment you give particular values to y0, y1, and y2, you would have like the actual number for the first derivative at the nodes. But in the linear algebra perspective, you can interpret this as a vector. Okay. So if you switch to linear algebra notation, like you can think about it this way. You have a vector which is p2 prime at -1, p2 prime at 0, at p double prime at 1. Okay. And the idea is that, I can regard this as as the result of a multiplication of a matrix times a vector y0, y1, y2. And that's kind of like the cool thing. So let me put here uh, y0, y1, y2. Okay. And then the matrix is just going to be literally the coefficients, that multiply each of the parameters, which you can think of as a variable. So it would be -3/2, 2, -1/2, then -1, 0, 1/2, and then 1/2, -2, 3/2. Okay, and so this 3 by 3 matrix is what's going to be called like the differentiation matrix for this choice of nodes in this particular case. So this would be the differentiation matrix. I'll call it D for differentiation. So this matrix will always be called D, but this is like the matrix associated to the choice of nodes that we made. Like, so associated to the nodes -1, 0, and 1. Okay, so just to be now, I can give you like more of an actual definition. So the idea is that so here's like more of a definition of what the differentiation matrix is. Okay, so what is the definition of the differentiation matrix? Okay, so again, the idea is that if you are given a list of nodes, if given n+1 nodes, right? Like they are x1, x0, x1 up to xn. So you have n+1 points, right? So if you're given n+1 nodes, you find the polynomial, right? As we were saying, you find the polynomial through xi, yi, right? Like for I equals 0, 1 up to n. And then what you can do is that if you can create two column vectors. Okay, one column vector is the vectors of the y vector, and the other vector is a vector of derivatives of the polynomial of these nodes. Then you build two vectors, two vectors. The first one, would be y, which would be y0, y1 up to yn. And the other one, I mean, we might call it y prime if you want. Like that's not a bad name. You, because it is related to the first derivatives, which would be, you know, uh, p prime of x0, p prime of x1, up to p prime of xn. Oh, let's call this polynomial p of x, right? Okay, and so the differentiation matrix is going to be a square matrix with the property that the matrix times y gives you the vector y prime. So the differentiation matrix is a n+1 n plus 1 times n plus 1 square matrix. With the property that y prime equals v times y. So in a sense, it gives you the values of the derivatives. That's why it's called like a differentiation matrix. It's kind of like a reasonable name. Or if you want to expand it out, you know, this thing equals v times y. Is that okay? Is that making sense? I'm about to do another example to kind of like make sure like finding it is very easy, like but I will do another example so that you have another one um to look at. Um and I put some on the problems, on the PDF problems, but they all kind of like follow the same idea. Like, so identifying that, and then I'll tell you in a moment why it's like a convenient thing to do. Um, but I just want to make sure like that the concept is kind of clear. It is a matrix that you can use to kind of like find the values of the derivative of the polynomial at these particular nodes. Okay, anyone? Okay, so let me give you another example just to make sure like this is making sense. So here's another example, which is actually going to be let's say that like this is related to the Chebyshev polynomial. So like if you remember, like a while ago we had talked about the Chebyshev polynomials, um, and there was this thing called the Chebyshev nodes, if you may remember, which you want they were like cosine of pi j over n for j from 0 to n. Okay. And those were like the points, the x values were the Chebyshev polynomial of degree like n would have would achieve take values plus or minus one. Okay. So for example, just to make something not too long, if you choose n to be 3, so like if you choose n 3 or n equals 3, the Chebyshev nodes are cosine of pi j over 3 for j equals 1, 0, 1, 2, 3. And that gives you cosine of 0, cosine of pi over 3, cosine of 2 pi over 3, and then cosine of pi, which if you write them, I mean, they're kind of like backwards. But if you write them if you plot them on the number line, that just gives you, this one gives you one, the first one gives you one, then the other one gives you one half, the other one gives you negative one half, and the other one gives you a negative one. Okay, and so you could think of those 4 points as 4 nodes. So this would be 4 nodes. And so kind of like you could find the different, like the problem could be to find the differentiation matrix for those nodes. So like the goal, like the problem would be to find the differentiation matrix for these nodes. Okay, so as I was saying, in this case, you have to find the polynomial first. In that case, for something like this, I would give you the polynomial because otherwise the problem is too long. Um, but you just find out the polynomial. You find out the polynomial. In this case, is you know -1, y0. But I'll give you it both in Lagrange form and expanded form so that you have both of them, you know, and then you choose which one you want to work with. But I'm just writing it out in the Lagrange form because that way someone may want to verify it more quickly. Okay. But yeah, like usually, like in simplified form, it's um, you know, a bit easier to kind of like work with it. Uh, Actually, give me a second. If I have if I can, no, no. Let's see. I'm just trying to see if I can find like long version I like in my notes. Let's see. Yeah, so like like if you were, I mean, again, like this would take too long, so I would just give it out in both versions. But if you were to do all the multiplications and combine them, you could also write it out this way. Okay. So the way I'm writing it in each line is kind of like, this is the cubic power, the cubic part. This is the quadratic part. This is the linear part, and this is the constant part. Okay. So again, like the point of these problems is to find the matrix itself. Like the polynomial, we already have many other problems where you have to find the polynomial. So I will just give you the polynomial. But then, you know, like so those are like the two versions, but like hopefully the first version makes it clear why you don't want to take the derivatives right away, right? Because if you were to take the derivatives right away, you have to apply product rule here, product rule here, product rule here, product rule here. So you see it is actually quite long to find the derivatives directly if you just do it from the Lagrange like approach. Um, okay. But once you have the polynomial, which again I'll give you, then you just find the derivative of that polynomial, which is not too bad. So you find the derivative. Okay, and so what is the derivative of this polynomial? Well, I mean, it's almost like there, like, it's not too bad to do. It gives you, it gives you 2 times negative y0 plus 2y1 minus 2y2 plus y3 x squared, right? And then plus 4 thirds y0 minus y1 minus y2 plus y3 times x, okay? Plus 1/6, right? Y0 minus 8y1 plus 8y2 minus y3. Right? Well, which is kind of like normal, like that's not too bad to find. Um, and then, okay, then comes the part where once you have you know, once you have uh, the polynomial, then or sorry, like the derivative of the polynomial, then you have to evaluate it um, at each of the nodes. Okay, so you evaluate the polynomial at -1, you evaluate it at -1/2, at 1/2, and at 1. I guess if you wanted to, like in practice, to do the evaluations, um, you can yeah, maybe let's talk about that for a moment. It can be more convenient before you evaluate to re-express a polynomial a bit differently. So I'll kind of like re-express it, like kind of like by grouping together the terms that have each of the parameters. So what has the parameter y0? You could think of this as being y0 times um, minus 2 x squared plus 4 thirds x plus 1/6. Okay, and then what has y1 with y1? What has y1? It would be, there's a 4 here and then an x squared. So you get 4x squared and then minus 4 thirds x. And then what has an y1? Minus 8 over 6. So minus 8 over 6. Then what has a y2? The stuff with y2 you have um uh -4 x squared. Then with y2 there's also a -4 thirds x, and then with y2 there's also an 8 over 6, right? 8 over 6 here. And last one, what has a y3? A y3, what has y3? With y3 you have a 2x squared, so you have 2x squared. And then you have 4 thirds times x, so 4 thirds times x. And then you have minus 1 over 6. So you see, it is the same polynomial, but it's kind of like factored in a different way, where kind of like you're grouping together the terms with y0, grouping together the terms with y1, and then grouping together the terms with y2 and y3. Okay, that makes it a little bit easier to kind of like identify when you evaluate the nodes, because that way you only have to kind of like evaluate each of these ones for different values of x. Um, So for example, I mean, this is pure arithmetic. There's, you know, not worth pointing to it right now, but like, then you just plug a particular value for x and then you start finding the answer. So like, you would find, it's a bit of like a bit, mm, you evaluate this, like for example, a -1, and if you evaluate a -1, you'll find negative 19 over 6 y0 plus um 4 of y1 minus 4/3 of y2 plus 1/2 of y3. Okay. And then you do the same for -1/2, 1 and 1/2. So this and -1/2, it would be negative y0 plus 1/3 of y1 plus y2 minus 1/3 of y3. And then you do it for 1/2. So you get 1/3 of y0 minus y1 minus 1/3 of y2 plus y3. And the last one would be that you do it for 1, and then you get, if you do it at 1, you'll get -1/2 of y0 plus 4/3 of y1 minus 4 of y2 plus 19 over 6 y3. Okay. And so what is the differentiation matrix? The differentiation matrix is just literally what you get by copying out these coefficients. So these are the coefficients in the first row, these are coefficients in the second row, third row, and fourth row. So once you have done all of this work, the finding the matrix will be easy, because so basically the way to read this out is saying, so if you read it in matrix notation, this is saying that p prime of -1, p prime of -1/2, p prime of 1/2, and p prime of 1, you know, that's going to be a matrix times y0, y1, y2, y3. And what are the entries? The entries are exactly what I was just telling you. So these would be -19 over 6, 4, -4 over 3, then 1/2, then -1, 1/3, 1, -1/3, then 1/3, oops, -1, -1/3, 1, and the last one would be -1/2, 4/3, -4, -9, and then 19 over 6. And so this is the matrix D. Is that okay? Is that making sense? Which again, I said you could write it in this notation as y prime equals d times y. In like, matrix notation. Like this is a vector y prime, and this, or p prime, like I could also have called this p prime, I suppose. Is that okay? Questions about it so far, so good? Okay, so now I can tell you something that's kind of like cool about this matrix, because I still haven't said what is one of the nice properties that it has. So what is a nice property of this matrix? Okay. What is nice about a differentiation matrix? Well, imagine that I asked you what does d squared times y correspond to, right? So what is, for example, what is d squared times y, right? So by that I just mean what, like, you square the matrix and multiply that by y. So what this would be, right? This is the same as d times y, right? So I don't know if this is kind of like anyone wants to take a guess, but again, when you multiply the differentiation matrix by y, that gives me the first derivatives of the polynomial at the nodes, right? So what do you think happens if you were multiply this by y again? And what should that give me about the polynomial? Anyone wants to take a guess? So this gives me the first derivatives, right? And the differentiation matrix kind of like computes the derivatives, right? So what is the first derivative of the first derivative? Well, that should be the second derivative, right? So the square of the so what this will give me are the second derivatives of the polynomial evaluated at the nodes. So this is going to be you know, p double prime, you know, like, well, in this case this is completely general, like, at x0, p double prime at x1, and p double prime at xn. So the point of having the differentiation matrix is that once you start taking powers of it, then you kind of like find, you can easily find all the other derivatives of the polynomial. So in general, so more generally, let's see. Um if you take the differentiation matrix to some power of y, sorry, if you take the differentiation matrix to some power and multiply it times the vector y, that gives you the mth derivatives of the polynomial at those nodes. So this would be the p sub pm of x0 up to pm of xn. So these are like, it's kind of like the mth derivatives of the polynomial at the nodes. Okay. So kind of like the nice thing about the differentiation matrix is that once you found it, if you did the hard work of finding it, then you can kind of like use it in many different places because it only depends on the nodes. And so it's kind of like ready to go to be used in different problems. And also its powers kind of like give you information about the higher derivatives of the function. Okay. Um, okay, so this is kind of like the last topic for the course. Like again, like that's the last thing I will include, like how to find the differentiation matrix. At least I'll take just 10 minutes to kind of like tell you like a kind of a nice application so that you see that how it's used in practice. But I won't ask the application because as you'll see, it takes, it's just like a bit too long to, if you actually wanted to do this nicely, it takes forever. But at least I'll tell you like an application so that you see how this is related to differential equations. So this is related to what's called like a boundary value problem. So, but it's like a very interesting application. So I just wanted to tell you a little bit about it. So, And this is like a very common way in practicing how like differential equations are solved. So this is one of the key ways to solve differential equations. So like on Thursday, we were talking about initial value problems, which is where you can like specify, what the function is doing at an initial time. So that is one class of differential equations. As I was saying, like differential equations can like break into two families usually. They have like the initial value problems, the IVP, and the boundary value problems, which are like the ones that I'm about to talk about. Um, so as kind of like the word says, like in a boundary value problem, you just specify what you want the function to be doing at the boundary. So, like one example, is that maybe you have like an interval a comma b, and you're trying to find a function. Okay, so you're trying to find a function that satisfies a differential equation. So you're trying to find, but instead of saying what it does at an initial time, you give some information of how the function is behaving at the endpoints of the interval where you're trying to find it, subject to information, to conditions on to extra conditions on what it's doing at the endpoints. What it's doing, it is doing at x equal a, at x equals a, and x equals b. And there are many ways to do this. Like if you ever take partial differential equations, this is something that's done very often. So there are different types of boundary value problems. Some are called Dirichlet boundary value problems. Those others are called Neumann boundary value problems, or combinations of those. This is like used a lot. Like this is like the bread and butter. If you ever take a class in PDEs, like this is something you do. But like just to give you like a super quick example, just to show you how this would work, like. Let's. So, like, what this is saying is that in this type of problem, what you're trying to find is you're trying to find a function whose second derivative equals minus pi squared times the function. Okay, and subject to the requirement that at -1 and 0, the function equals 0. So, kind of like if you kind of like draw -1 and 0 here, like the function basically kind of like, I don't know how it would look like, but whatever it does, you're forcing it to be equal to 0 at the boundaries. Um, so like an analogy for this could be like, you have like a bridge, and at the endpoints of the bridge, you have like some sort of like support system that doesn't let at the endpoints, and the bridge doesn't like change its height. But when weights travel through the bridge, like cars or something like that, the bridge is allowed to bend, but not at the endpoints where you have some columns maybe that force it to kind of like stay in position, right? But elsewhere on the bridge, like like the height of the bridge could change, like the displacement with respect to some reference level. So it's kind of like a natural boundary condition to have. um, and like here, like just by trial and error, I mean, of course that's not how you would do it, but a solution to this problem, you could check. If you wanted, you can check that what is what is a solution to this problem? Like sine of pi x solves this problem. Why? Because if you take the first derivative with respect to x, you get pi cosine of pi x. And if you take the second derivative with respect to x, you get minus pi squared sine of pi x, right? So you can see, and and y of 0 would be sine of 0, which is 0, and y of 1 would be sine of pi, which is also 0. So in this case, you can kind of like check by hand, you know, in this case, you can kind of like check by hand that these functions solve the problem. But the idea, again, because we are in numerical analysis, of course, you don't know what the function is, like you don't know what the solution is. So in numerical analysis, what you would do is like actually try to approximate the solution, right? So how would you try to approximate the solution? And I will just, again, I'm not going to ask this on the exam, so I'll just kind of give you like a super quick idea of how it works. So how to find an approximate solution. Well, so again, because we're working on the interval -1 to 1, that's kind of done by on purpose. Then, like for example, you could choose the Chebyshev nodes. Okay, so one option is like you choose a value of n, choose a value an integer n, and you find the Chebyshev nodes for and you find the Chebyshev nodes for that integer. Okay, and you find the Chebyshev or you use the Chebyshev node. So for example, if n equals 3, we already talked about those, right? So for n equals 3, the nodes were, okay, the nodes were like -1, -1 half, 1 half, and 1, okay? And with those nodes, then you can find the differentiation matrix. Then the next step would be to find the differentiation matrix for this node, which you already had from the previous example. Okay, I will just copy paste it because we already wrote it before. So the differential, oops, like this was a differentiation matrix. Okay, and if you notice, like the differential equation, like the idea is instead of solving the differential equation directly, you try to solve it at the nodes. Okay, so you try to solve. So then the idea is to, instead of solving, uh, you know, at every value of x, right? Okay. Then kind of like you discretize the problem, which is how you say this. You kind of like make it a finite problem. So you try to kind of like just solve this equation at the nodes that are on the interior of the interval. So you solve it, try to solve instead. You solve instead. Like, what is the discrete version of this? Again, like the second derivative gets replaced with the differentiation matrix square. So you try to solve d square of y equals minus pi square of y, for example. And that turns it into a linear system of equations that you need to solve. Okay? Or y, because y here would be, it would have been y0, y1, y2, and y3. Okay? Um, so you're trying to solve for those values because those are the y values that the function would have at the nodes. The only thing is that you want the solution to respect the boundary value condition. So you force y0 and y3. Y0 and y3 correspond to the values at the endpoint. So you do force those two to be zero, so that the boundary condition is respected. So actually, you know, you end up just solving 0, 0, y1, y2. So you solve the equation. So you solve that. So again, like where y0 and y3 is 0 to enforce the boundary condition. And so you only end up having to solve a system for, you only end up having to solve a system for y1 and y2. So you end up having like to solve a system of equations for y1 and y2. So in this case, you solve a linear system. Okay, so again, I'm not going to solve it or anything. I'm just going to show you I'm just going to show you some pictures because, as they say, like pictures, like an image is like 1,000 words, right? So basically, let me go to GeoGebra for a second, just so that you see how it looks, because it's kind of like nice. Um, okay, okay. So here's the thing. Oh, sorry. Let me share the correct thing, like GeoGebra. Okay. So here's the situation. So again, this is the interval -1 to 1. The curve in red is the actual solution. So what I'm showing you right now is the actual solution to the differential equation. So you see the boundary condition like is satisfied because at the endpoints is 0, right? So what I'm saying is that forget about the solution because you don't know it. You're trying to approximate it. So what you do is use like the Chebyshev nodes and you solve the system of equations. So if you solve the system of equations, you'll find that a negative 1/2, that's one of the nodes. Like the value of y1 had to be minus 1.23, which is what you see here. And then uh, at 0.5, the value had to be 1.23. So this is y1 and this is y2. And y0 and y3, what I was telling you is that y0 and y3 are set equal to 0 so that the boundary condition is respected. So once you have those 4 points, you say, okay, like 4 points is not that much, right? Like what do you do next? So what you would do next is you find the polynomials through the points. So you find the polynomials through these 4 points, and then you find this polynomial. Okay, so that's the polynomial that goes through these points. And if you compare it to the actual solution, I mean, like it's not quite the same, right? Like definitely they're not the same curve. I mean, they're never going to be the same curves because a polynomial of finite degree is never going to be equal to a sine. But at least certain qualitative features are already captured by just using 4 nodes. So kind of like the idea is that you can imagine what happens if you had done this same process for more nodes, and I can show you that quickly. I asked ChatGPT to do it for me. Um, let's see. Okay, so um, so for example, right. Like, okay, so let me see. I asked it like to do a bit different cases. Okay, so let's see. Okay, so for example, if you do this with 15 nodes, you kind of like get the again when you do 15 nodes, you would find the differentiation matrix for those nodes. You square the differentiation matrix. You impose the boundary conditions for at y0 and I guess 15 right now, and then the rest of the points are like these ones that you see here. So then you would have to find a polynomial that passes through these points. And the thing is, like, if you were to find that polynomial that passes through these points, like that is almost like in this, I mean, it's almost indistinguishable from the actual solution. So in fact, like already for like 15 nodes, like the solution like is almost like the same. Like if you kind of like go here, like you can see the error terms, they involve 10 to the negative 12. So it's basically or 10 to the negative 16. So it's almost like indistinguishable from the actual solution. So like then I asked it to kind of like show part like smaller values so that you can see a little bit more of the error. So um, like this is for example with n equals 5, how or with n equals 8, how the polynomial looks like, and through those nodes. But I don't. Did I ask it to? Oh, here it is. With n equals 5, those are the points in orange that you would get, and the actual curve would be in blue that you see here. But once, like for example, when you go to n equals a, you see like the points like start getting closer and closer to the actual curve. So my point for bringing this up is like in certain problems very quickly, once you have like 10, 15 nodes, like like the actual solution and the polynomial solution that you get from this approximation, they are very close to one another. So, but it is an idea that generalizes to many other cases, like like again, like it's used a lot in meteorology and other, like whenever you have like a partial differential equation, this is one of like the ways to try to solve it. So I thought, like, I mean, it was like an interesting idea to kind of like wrap up like the topics of the course so that you see like how really like like all the stuff that we have talked about polynomials is kind of like a very powerful tool, and like you can adjust it very nicely to many different problems. Um, so as I was saying, the idea for tomorrow is I would just have office hours, so there's no class tomorrow. Um, and then I will make available the quiz now in case anyone wants to take it. But if not, I mean, I can also stay here like to answer questions. But look at the study guides, look at the mock exams, and then you would be fine. Look at the practice exams. But if you want to ask me anything about anything, like I also have be here like during office hours, like over Zoom. So, but yeah, also if you want to ask me something right now, that's fine. I can stay for longer. Anyone? Any questions?